Hey, what's up, everybody? So today, geometric sequences. So very similar to arithmetic sequences, which we did last week. Now it's geometric, okay? So last week, arithmetic was adding, subtracting every term in the sequence, or to get every term in the sequence. This week, geometric sequences, they multiply and divide each time, okay? So you're multiplying and dividing by the same number each time. So multiplying by 2, multiplying by 10, dividing by 3, whatever. Those are geometric sequences. Those are very common in the real world. I've got some examples here. They're all over the place. Anything that's exponential growth or exponential decay, those are geometric sequences. So that stuff we talked about earlier this semester, those are just geometric sequences, those exponential functions. So, money in a savings account, population growth, bacterial decay. Obviously, big one right here, right now, coronavirus, the growth of number of cases is generally thought to be an exponential function, which would be a geometric sequence. Last one, a height of a bouncing ball. So like ball that starts up here, drop it, bounces. Those heights, okay, each time, that's going to follow a pattern that's going to be dividing by the same thing every time, depending on the type of ball you have. Okay, so that's where some things where they show up. Obviously, there's lots of other places. All right, so some important terms and notation. So some of this is going to look very familiar. Okay, these top three, exact same thing as with arithmetic sequences. Okay, n is our term number. All right, that's just, if I say find the 10th term, then we plug in 10 for n in the formula that we're going to find. When we say a sub n, that's just how we define the sequence or the formula for it. So that's like, if I want to find the 10th term, we'd say a sub 10. We put a little 10, you'd write it like that. Okay? Or if I said a sub 5, that'd be the 5th term, so a sub 5. So the nth term, so just to find any term number, a sub n. Okay? A sub 1, so if I have a subscript of 1, that's kind of a special one. It's our first term, known as, same as before with arithmetic sequences, initial value, okay, which is our first term. All right, the new one, so with arithmetic we had a d for common difference because we were adding the same number at the same difference each time. Now we have r, okay, which we call the common ratio, which we think about that as like the rule of the sequence. Really, though, what it is, it's whatever we're multiplying or dividing by. Okay, so if I'm multiplying every time I'm multiplying by 5, then my common ratio r would be 5. If I'm multiplying by 20, common ratio would be 20. Okay, so that's some of the important terms. Now moving on to the actual formula. So this should look kind of familiar to the arithmetic, just a little different. Now we have an exponent involved here. But basically all you're going to be doing is finding what the numbers are, plugging them into the formula, typing them into a calculator. Okay? So if you look right here, this is our explicit formula. Lets us find any term in the sequence. Okay? So here's our example. So we're going 2, 6, 18, and so on. So think about, all right, well, first, a sub 1, that's my first term. Well, first term there is 2. Okay, sometimes it's hard to find r in these, okay? You have to think about, okay, well, what's being multiplied or divided each time? So if it's getting bigger, then we're multiplying, okay? In this case, from 2 to 6 to 18, you can probably figure that out in your head. But if it's something that's a little complicated with a decimal somewhere in there, easy way to find out r, if I want to know what r is, just do 6 divided by 2, the second term divided by the first. Okay, obviously that's 3, or you could do 18 divided by 6. Okay, the third term divided by the second. Okay, and that's an easy way to find out r, to find what you're multiplying each time. Just do the opposite. Okay, so in this case r is 3. So all I do now to find my a sub n, my formula, use the formula up here. Okay, so a sub 1 we defined as 2, so put our 2 there. R is 3. Okay, and I like to use parentheses. You could use just a multiplication symbol here, that's fine. Okay, whatever you want, just know you're multiplying. And then my exponent always stays as n minus 1. Okay? So then you might be asked, find the 12th term. Okay? So if I want to find the 12th term, a sub 12, so 12 is my n, so we just plug in 12 for n. Okay? And we just need to do that in the calculator, because some of these are going to be pretty big numbers, depending how, putting 12 up there is going to give us a big number. Just make sure when you're doing these, depending on your calculator, make sure you remember order of operations. Okay, we've got to do the exponent first. So, be a real good idea to check this right now, whatever calculator you've been using at home, if it's on your computer, on your phone, whatever. Check this, make sure, type this in. You should end up getting 354,294. Okay. It's a pretty big number, obviously. So, that's basically what this is. I'm going to give you one more example here of a kind of real life situation. So, here's our example. So, let's say we have a city of 200,000 people. All right, 100 people in the city right now have tested positive for coronavirus, and let's just pretend no one's social distancing. All right, no one's staying away. We're all hanging out with friends and doing all kinds of stuff. Our number of positive tests is doubling every day. Okay, so we want to figure out, okay, after 30 days, how many people theoretically would be testing positive? Okay, so if this is doubling every day, that tells me it's a geometric sequence because it's multiplying by the same thing, and our common ratio, if it's doubling, multiplies by 2. Okay? So I can figure out my sequence. All right, this is what it would look like if it's doubling every day. You can see it's going to get a lot of people pretty quick. So a sub 1 would be my 100. So I can write my formula. So a sub 1, I'll just write out the formula here first. So a sub 1 times r to the n minus 1. Okay, a sub 1 is 100. R is 2. So there's my formula. So that's going to let me predict how many people would have it after a certain number of days. Okay? Eventually we kind of have to think about, all right, we have a city of 200,000 people, so we can't have more than 200,000 people in that particular city that has it, but just for example purposes is what we're using. So after 30 days, so all we're going to do, okay, the left side here, this a sub 30, all that's telling us is we're finding the 30th term. We don't do anything on that side with the 30. All right, all the calculations happen on the right side. So we plug in 30 for n, okay? And this is going to give us a crazy big number, all right? Because think about if I'm doubling this every time, so this sequence was 100, 200, 400, 800, 1600, 3200, and it's just going to skyrocket eventually. It ends up being, write this number out, so you can see a ridiculously big number. Okay, so obviously the city only had 200,000 people. It's not going to get there. Okay, but everybody will then have it eventually. Okay, so not ideal, and they would probably spread it to other communities and whatnot. But that's how geometric sequences work. All right, so you've got a go formative to do. Let me know if you have questions on it, or if you have any questions on this video, shoot me a message. Hope you guys are all doing well. I'll see you guys later.